Hello everyone. In this video that is going to be short, I want to show you how to simulate a mass spring damper system in CoppeliaSim. One of my students today asked me about it. So it was a suspension system for the wheel of a robot, and she asked me how can I put the suspension on the robot, right? Because you don't have necessarily an element here that is called a spring or damper. Now, one of the things you can do is when you add a joint, as you know, so let's say in this case a prismatic, because it's a prismatic system, one of the things you can do is in the dynamic properties dialog, instead of the control mode free, you can make it control mode spring. But I tried it. I did not get really much of a good result. Maybe I didn't do it right, but I'll try to do it. But I found that using a script does a much better job. So this is what I did here. I have two blocks. The base block that I made it static, it doesn't move. This block that is dynamic and it can fall down. I put a prismatic joint between them, and if you look at my prismatic joints, I left it as free. So the only thing it does, it forces this object to just go up and down and not deviate and fall and anything. So it just controls the motion in one direction. And you can see that I made this block called mass a child of this prismatic joint that I call it guide, and guide the child of the base. I added a dummy to the mass, so when it goes up and down, I can plot the Z position of it. Let me show you. There we go. So you see, this is the underdamped behavior, and this is exactly the response of the system. So how do I do that? Let me show you the script that applies the force of the spring and the damper. So if you go and look at this, so here it defines the two masses, the base and the mass. You define your spring constant, you define the damper, you define a original length for the spring, which is here 0.5 meter. And then in the actuation, you see you get the position of both of these masses with respect to the word -1. Then each one of them has three components, x, y, z. You subtract these x, y, z's and you form this dx vector. This dx is basically the same as p2 minus p1. It's the relative position between the two. And then here you take a square root of that to get the distance between them. And if this distance is very small, you are going to not do the rest of it and return. Why? Because here you want to get the unit vectors for this relative vector. And here you are going to divide the components of this dx vector by the length of it. And if this is very small, you're literally dividing by 0, and that's not what you want to do. So here you're trying to limit it to so much. So these are the unit vectors. Now, why do you need the unit vectors? Because the forces of the mass and the spring and the damper are applied in this direction. And you might say, well, in this direction, the object is only going up and down in the z direction. So what you could do is get P1 and P2, but then define, for instance, P1z as P1 number 3 and P2 as P2z as P2 number 3, and then work with those. Yes, absolutely, you can do that. So this is a little bit more general. This can work for a scenario that this mass relative to this one is not necessarily only moving in the z direction. It might have some x and y motion as well, and this prismatic joint might not be perfectly straight. It might have angle. So even if you tilt this now and bring this to the a little bit off from the center, this code will still work. Okay, so it's not just designed for upright position. And so if we go back here, we have the unit vectors, then we get the velocities of them using get object velocities. Why do we need velocities? Because we need them for the damper force. Why do we need positions? Because we need them for the spring force. So now we are going to find the relative velocity, which you can see it is the subtraction of the two velocities in the unit vector directions. Again, here it's written for a general 3D case. And now you see that the total force is going to be the damper constant times V relative plus a spring constant times the current length minus the original length. and they are both negative. And now you are going to apply these forces to both objects by multiplying this magnitude in the direction of ux, uy, and uz. So you are doing a force decomposition here. And you apply negative of them to mass 1 and positive of them to mass 2. So you have action and what? Reaction here. And finally, once you have these forces, you are going to use this new function that we have called sim add force and torque. And you are going to apply what? You are going to apply these forces. And you might say, what are all these zeros? Well, these are the torques. Remember, this one is to apply forces and torques. In this case, we are only applying forces because they are all passing through the center of mass, so there is no torque. Therefore, we can add them all 0, and this is the syntax of this. Okay, so force is a vector and torque is a vector. The same goes here for this top line. You might say, what is this underscore that you have here? This means this element, I don't care about it. All I care about is linear velocities. And you might say, well, does this function get object velocity? Does this one give us the angular velocity? And the answer is yes, it does. It gives you both of them. But again, since here we only want one of them, we only get the linear velocities, okay? But you can get the omegas of the object too, and that is the power of this command. So this is a great command, this one is a great command, and this one is really interesting. And as I said, this is working for a perfect 3D case. So this is the script for the simulating the spring and damper force, and this is the spring for plotting the z position, right? So you get the handle of the dummy, you get the handle of the graph, you start a stream or a curve, where the first one is the handle of the curve, the second one is basically the name of the stream, then we have the unit, and then we have options, then we have the color here, you say it's red, and then cyclic range and so on. So in this case, it's really, we only care about the name and the color, okay? And here, if you want, let me add that for you here. That is the syntax of it. I copied it. And now that the initialization starts here, we get the position of the dummy with respect to the world. And then we get the third component, which is the z. Then we say, hey, go ahead and add this value, which is called z word, add it to the stream called z in the graph called graph. So push this number through that stream, and then you are going to also pass the time of the simulation to the graph, because this simulation is z versus time. So you need to have time here. And this is what you will get, z versus time. Okay, so hopefully if you haven't done mass spring damper simulation in the past, this two codes that I'm gonna share with you allow you to be able to perform it. Thank you so much for your attention, and I'll see you in the next video.